So I'll be speaking about causal inference, in particular with hidden variables and the inflation technique, which essentially solves the problem of causal inference with hidden variables. If you don't know what these terms mean, don't worry about it. It shouldn't really be necessary because it's really all fairly elementary. So let me start with this picture. So some of you, if you grew up in the 90s like myself, you might remember this video game. It's called The Incredible Machine. So you basically have to build a system that achieves a certain task. So in this case, you're supposed to make this mouse end up in here, which is kind of its house or something, I guess. And you have these things available. And you can place these in an arbitrary location. Then you have to somehow, when this machine runs, you have to achieve that a mouse, well, actually lands in here. And this is the type of problem. If this is a problem of network synthesis, essentially, you're given pieces of things, and you need to assemble them in such a way that you achieve a desired functionality. And so this is just in the flavor of the problem. This is similar to the problems that I'm going to talk about. But there's a different way to think about it. And so let me now try to phrase or explain a problem which a priori sounds a bit different. And so this also goes back to the linguistics things that we've heard about. Just to give a concrete example, this would just be one particular application. Let's say you look at a grammar or maybe the vocabulary of some languages, and you notice that there's some correlations between these. So then you would think that, well, there has to be some common ancestor of these languages, some language that has existed in the past, and from which all the current languages that you're looking at are in some way descendants. And so this is made more formal by this Reichenbach's principle, that two random variables, A and B, that are not independent, they must have a common ancestor. So when we speak about common ancestors, this is already talking about causal inference in a sense, because then we're talking about causality, so which things have caused which other ones or have influenced which other ones. And so this is basically the subject that causal inference refers to. And more concretely, the type of, a more concrete problem that I want to look at is if you have now three variables. No, sorry, let me say that. So the two variable case is fairly simple. Because, well, if there is some correlation, then you would conclude that there is some common ancestor, which may be A or B itself. But now if you have three variables and you notice some correlations, the situation is much less clear-cut. And for example, you could try to infer, is there a common ancestor to all three? Was there some variable or some event or something in the past which has influenced all three of these variables? And so one can try to find criteria to detect this, to basically prove that this must have been the case using this kind of assumption that all correlations must be explained by common ancestors. And so the null hypothesis, so if this is not the case, if there's no common ancestor for all three of them, that means there could at most have been a common ancestor for every two of them. So the null hypothesis would be that any two of them have a pairwise common ancestor. And so now let me try to relate this back to the network synthesis problem. There's kind of two perspectives on this type of problem, this type of mathematical problem, that you are observing, or no, we are given, let's say, a three-variable distribution, and we want to know whether we can model it using this kind of graph. So using 6 variables, so this represents the null hypothesis. using 6 variables, such that, well, A is a function, so in general a stochastic function of x and y, B is a stochastic function of y and z, and C is a stochastic function of x and z. So this includes both the problem of explaining or having observed data and trying to find an explanation for that in terms of common ancestors, so which would be the case in the language example, but it also includes the problem which is more of the type of synthesis or generating a distribution. And so this, from this perspective, this is about complexity theory, if you want. So because then so suppose you want to generate some 3-variable distribution ABC, and you wonder what kind of network do I need in order to generate that. So then we're talking about things like circuit complexity. And so mathematically this is the same kind of problem, and so causal inference addresses both of these things. And so this example of this triangle causal structure, that's what I want to use as a particular example for our technique, which solves this problem. But the technique is very general and also outlined in generality. Okay, so to make it even more concrete, let me take a particular example. Namely, suppose these A, B, and C are all binary variables, so they take value 0, 1. And the distribution is such that they are all perfectly correlated and uniform. So that means the event 0, 0, 0, the outcome 0, 0, 0 occurs with probability 1/2, and 1, 1, 1 also occurs with probability 1/2. And then I guess it seems kind of intuitive that it should not be possible to generate this distribution using this causal structure, because there's really some 3-way dependence here that cannot be reduced to just pairwise things. Okay, but how does one actually go about proving that? So this is now the first example of the technique that we've developed for this problem. So namely, let's take this graph and modify it a little bit, kind of cutting it up and rearranging things. And so instead of looking at this graph exactly, I want to look at this one. So how this arises is basically I take 2 copies of y, or I kind of cut y into 2 halves. Then it becomes a y1 and a y2, and those split apart. And then I get something that I can also draw in this way. Okay, so this is a new directed graph. And yeah, these other labels here for these other variables are just, you can basically ignore these. The relevant thing is now that here we have a y1 and a y2. And now we can assume that our given distribution can be generated in this form. Let's just assume it for the sake of contradiction. And then if this is possible, so if I have a realization like this, then I can do this construction and also look at this graph. So I can take the same distribution for these root variables, x, y, and z, and I can take the same dependence of A on x and y and just put it here. And I can declare that this A2 I want to depend on y2 and x1 in the same way as the original A depended on x and y here. And so now I get a new 3-variable distribution over this A2, C1, and B1. And so now one can ask, well, what do we know about this new distribution? The essential observation is that we can actually say quite a lot about this, although we don't know what the x, y, and z are. And I mean, they're purely hypothetical anyways, but in general, we don't know the entire, we don't know the full distribution, but we can still say something about some of its marginals. Namely, if we just ignore B, and if we only look at A2 and C1, then the y1 doesn't matter. It's just as if this part was not there, right? So then we only have the A2, C1, and these, their parents. And then this is just the same as if we ignore the B here. Then the subgraph, namely the subgraph formed by A and A, C, and their parents, is exactly the same in here as it is in here. So therefore, yeah?
When do you say that a graph can realize a probability distribution?
Yes, so this,
what does that mean for you?
If you know what a Bayesian network is, then this is what I mean here. That here I have some observable variables, which are the ones that are drawn as triangle nodes, and a chain distribution on these. And I have this can be realized if and only if there is a Bayesian network on the entire graph that marginalizes to the given distribution on these observable nodes.
So it looks like this Boltzmann machine with the hidden variables.
I'll get to that. Yeah, exactly. Yes. So the restricted Boltzmann machines are basically of this form, where you have a layer of observable nodes and a layer of hidden nodes, and then there's a bunch of arrows from the hidden nodes to the observable ones.
That connects to my second question. Like you would suppose then that the probability on A or the probability on C can be obtained from marginalizations of the probability on X. So this directionality?
Not marginalization, but there is, so basically you can, one way to express the joint distribution that you have on a Bayesian network is essentially by convoluting all these, all the ways in which all the variables are functions of their parents' stochastic functions. So there's basically a conditional distribution for C given xz, a conditional distribution for B given yz, likewise for A, and you get the full joint distribution if you convolute or if you just multiply these conditional ones with the joint distribution of x, y, and z. And these three are independent, so you just take the distribution of the original ones and take their product. And so overall, yeah, maybe I should have, let me write this down, because this is kind of important. So the overall PA... So the overall distribution of what we got for all the 6 variables is, well, we have x, we have the distribution of y, the distribution of z, and these are independent, so we just multiply them to get a distribution of x, y, z. And now A is a function of x and y, so to also compute the joint of A, x, y, z, I'm just going to have to multiply by the probability, well, or this conditional probability distribution. This is part of the data that specifies the particular realization. These conditionals. Okay, so this is for A. I guess I should have written this down here. B depends on y and z, and C depends on x and z. And now I only want to look at a joint distribution of A, B, C. So that means I'm going to have to form the marginal sum or integral over the values of the hidden variables.
Okay, thanks.
So having a particular realization means that a PA, B, C is given explicitly in this form for certain these conditionals and distributions of the x, y, z. And so these graphs are just a nice way to write this down. Okay, yeah, so in this new graph, which then we're going to call an inflation graph, I'm basically taking the same distributions and conditionals and rearranging them in a different way. And then a priori, I don't know what I will get overall, but I can at least say something about the joint distribution of A2 and C1, because the induced subgraph of these variables and their parents is exactly the same. So yeah, we can conclude this, and likewise for B and C, the induced subgraph is just the same as in the original graph. But now we can say even more. We can also look at what happens between A and B. And so A and B do not have any common ancestor in their past. There's nothing that has influenced both. So in this graph, A and B are going to have to be independent in any distribution that is compatible with the graph. Yeah. Okay, here actually, so yeah, so this equation had this in a different.
Y1 and Y2 are copies.
Yes, are independent copies, so have the same distribution but are independent.
Okay, I see.
Because yes, so this is kind of encoded also in the graph, right? Okay, so from that, yeah, from all these independences and A and B then not having a common ancestor, we can infer this. And so now we have three equations. We know the marginal distribution of AC, the one of BC, the one of AB, and now it turns out that there's no joint distribution for these new A2, B1, C1 that would have these three marginals. Because, well, here we know that A and C are perfectly correlated. So when one of them is 0, the other one is 0. B and C are perfectly correlated. When one of them is 0, the other one is 0. That implies, so a perfect correlation is transitive. That also implies that A and B are perfectly correlated. But now this is in contradiction with this independence. And this is a simple way to show that this joint distribution that we were starting out with is incompatible with this triangle causal structure.
How would you modify the argument if you perturb this distribution a bit?
Yeah, that's on the next slide. So we can. This is kind of very only works for this particular distribution. But the nice thing is that we can also make this argument quantitative by deriving an inequality that must hold for all distributions that are compatible with the triangle causal structure. And this is basically the same reasoning. And so a bit more explicitly, no, it's a little bit more convenient for writing down the inequalities to use the outcomes plus and minus 1 for these variables. It's just a reparameterization or relabeling. Right? So in terms of plus minus 1 valued outcomes, there is an inequality, a linear inequality for expectation values that holds whenever your three variables A2, C1, and B1 have some joint distribution. This is this is not hard to see. I mean, you basically need to plug in all the 8 possibilities of plus minus 1 valued assignments and check that it holds in these cases. And then by linearity, it means that it also holds for all joint distributions because every joint distribution is a convex combination of these deterministic ones. Okay, but now here we can again use the same observation that we actually know these what these expectation values are, or we can re-express them in terms of the original distribution P, A, B, C that we want to, for which we want to know whether it can be generated from the triangle or not. Yeah, I mean, so the AC marginal, this was what we had used before, is the same as on the original graph. So here I'm just going to substitute these expectation values, and likewise for CB. But now A2 and B1 are independent. So I'm going to substitute this by the expectation value of A2 times the expectation value of B1. But now again, A2 and B1 themselves are a single variable distributions, are the same as, again, as in the original case. So this is just the product of expectation values. So now making the substitution, we arrive at this compatibility, this inequality, that every distribution P, A, B, C that is compatible with the triangle causal structure must satisfy. And this is now a more robust version of the earlier argument. Yeah, and the nice thing about this is that we started out with a linear problem, a linear inequality, and here it becomes polynomial in the probabilities. Okay, so let me make another example, now this time slightly trickier. And starting with this, but so still on the triangle causal structure, and let's look at this distribution. So this is saying that exactly one of the three variables must be 1, and the other two must be 0, and then there's 3 possibilities remaining, which occur each with uniform probability. So here it may be much less clear. Is it compatible with the triangle causal structure or not? And for example, it turns out that if you also allow the outcome 1, 1, 1 and make all 4 of them equally likely, then yes, it is compatible and it's not so hard to generate it. But this one is still not compatible. And the proof is, well, uses the same technique, but the actual argument is a little bit different in the details. So instead of considering this modified graph, now I want to consider this one. So here again, we have 2 copies of x, 2 copies of y. No, we have 2 copies of each of the original root variables. And, well, a bunch of descendants. But again, we can assume that each of these variables depends on its ancestors in exactly the same way as in the triangle. Or in other words, assuming that we have a realization of this in the triangle, we just take its pieces and a bunch of copies of it and rearrange them. So this is like in my title slide, you know, in this The Incredible Machine video game, we were taking these pieces and arranging them in some way. Okay, and so then that results in these equations. So the first equation is just saying that on this induced subgraph is the triangle again. So here we have the full original distribution. The A1, B2, C2, where's that? Yeah, so B2, wait, is this right? Yes, right, okay. A1, B1, no, this is, right, yeah, okay. So the A1, A1, B2 part is kind of disjoint from the C2 part. Right? If you take their ancestors, look at their causal past, or everything that happened, if you follow the arrows backwards, you won't be able to reach any node that ends up both in C2 and in A1 or B2. So that means the A1, B2 joint distribution is independent of C2. So, but each of these two individually, say A1, B2, is again just this kind of part of the triangle, so it's S in the original one, and a C of course as well. And so now continuing like this, we find that, that we can express these 5 marginal distributions in terms of the things that we know. Yeah, and then again it turns out that these 5 marginal distributions are incompatible with the existence of a chain distribution for all 6 variables, A1, A2, B1, B2, C1, C2. And there's a bit more of an explicit argument for this, which is again kind of in a logical uses kind of tautologies and Boolean logic, if you want. Namely, by this equation, we can see that the event that A2, B2, and C2 are all 1 has positive probability because, well, yeah, we can just write down what the probability is. And here we see that each one of them has positive probability to be 1. Therefore, also that they all are 1 has positive probability. So that means whenever this happens, so one of the 2 variables is 1. Then we can look at what happens if the 1 variables. Now there's basically 2 cases that also one of the 1 variables takes the value 1, in any concrete run of the experiment, let's say, then we are in one of the first three cases. Then also one of these events occurs, right? Just depending on which one of them is 1. Okay, maybe 2 or 3 of them, but that's fine. Or none of them takes the value 1, so they all take the value 0, then we are in this case. So whenever this happens, one of these also must happen. And now we can just apply the union bound from probability and conclude that the probability of this event is lower bounded by the sum of the probabilities of these events. But now, if you go back here, and you can actually, you'll notice that you can actually compute the probabilities of all these events, and these all turn out to have 0 probability. Just because, yeah, it's just that A and B cannot both be 1. So this way you can see that this event has 0 probability. Well, this one had positive probability, and so now this is in contradiction with that union bound inequality. And so there's no time distribution for all the 6 variables, which would reproduce these marginals for this particular example. And therefore we conclude that the original distribution from here cannot be generated using this triangle causal structure. Okay. And again, we can make this quantitative now by deriving an inequality. This follows pretty much the same lines of thought by now writing the union bound explicitly as an inequality, so the union bound for these events. And just again substituting these known marginal distributions in terms of the right-hand side, and thereby expressing them in terms of the original given distribution PABC for which we want to find bounds. Yeah, and that's how we arrive at this inequality. And so this is another causal compatibility inequality for the triangle graph. Okay. Now let me get to the general technique. So the general method is a method for causal inference with hidden variables. And it's also fairly flexible. So I'm focusing here on the case when, let's say, the outcome, the observed variables all take finitely many values. The hidden variables are arbitrary. But one can certainly apply it in many different variations. I don't know, for example, with Gaussian variables. So we haven't looked at this, but it seems quite clear one can use the same techniques with, for example, Gaussian variables or other things. So let me focus on the case where the observable variables take finitely many values and the hidden variables are arbitrary, but just wanted to mention that it's in principle quite a bit more general. Okay, and so we start with an arbitrary causal structure G, by which I mean so a directed acyclic graph, which is what these Bayesian networks are all about. And there should be a distinction between observed nodes and hidden nodes, like these triangles and circular nodes that I had before. And then an inflation, which would be like this spiral inflation here, for example, would be another graph that I want to call G prime, together with a graph map from G prime to G, which is a map that takes nodes to nodes in such a way that it preserves adjacency. So adjacent, or whenever there is an arrow from some node A to some node B, then also there should be an arrow from pi of A to pi of B. And this is kind of indicated in this picture. I haven't told you what actually the map is, but this is kind of implicit in the labeling of these nodes. So basically the name of the node indicates where it goes in the original graph. So these two go to B, and the index then just indicates that these are, well, in the pre-image of B under that map.
In this example, for example, that is G prime.
Yes, yes, yeah,
So
right.
I can say y is unique. If I start from y1,
Uh-huh.
I have two listings of the path from y to b.
For the path from y to b.
There is two.
No, the lifting is the other way around. When you have a lift of b, when you choose a preimage for b, then you can go backwards in a unique way. But yeah, good point. Okay, so yeah, the map is kind of implicit in the figures that I'm showing. Yeah, so every such map is in particular vibration, which we were just discussing already, that whenever you take an edge in G and you choose a lift or a preimage of its target vertex, then there's a unique way to lift the entire edge. So there's a unique preimage of the source vertex that has an arrow to the given lift of the target. But it turns out that this is not sufficient to be an inflation, but to be an inflation we need a little bit more, namely that whenever we restrict pi to the ancestry, so to the entire causal past of any node, which means we follow all the arrows backwards and take all the backwards paths, then restricted to that, the graph map pi must be an isomorphism. Okay, and using this assumption, we can take a causal model on G, by which I mean just all specification of all these probabilities or a Bayesian network. So just a joint distribution. Yeah, I mean there's different ways of saying what a causal model is. You can either write it down with such a factorization, or you can say that it has to be a joint distribution that satisfies the corresponding Markov conditions. But so yeah, causal model is just whatever definition you prefer for distribution compatible with the graph. And now there's a canonical way to lift the causal model from the original graph G to the inflation graph G prime. And well, in the examples we've already used that. You just take all these conditional distributions that are present on G, and well, you just lift them to G prime, and then you compose all of these, or you convolve all of these to a new joint distribution, which lifts in general on a much bigger graph. Okay, and so then the crucial insight was that looking at this inflation graph and this inflated causal model, we can say something about some of the marginals of that. And so the set of nodes for which we know what these marginals are, these are given by the injectable sets of nodes that we call injectable. And those are precisely those for which when we restrict the graph map, then we end up with a bijection. Okay, yeah, and then in the causal model, the marginal distribution is exactly the same for the inflated one as for the original one. And so now if we have a distribution on, so this leads to this lemma, which is kind of the main lemma that makes the technique work. That if you have a distribution on the observable nodes of G that is compatible with that causal structure, so for which a realization exists, then if you take this inflated causal model and you look at its marginals on injectable sets, then this is compatible with G prime in the sense that this family of marginals admits a joint distribution that is compatible with G prime. And so this is a central observation, and it also means that we can, in principle, apply any method of causal inference on G at a level of G prime, and the inflation technique strengthens it to something that applies to a different graph. And when I say strengthen, it may not be clear why it gets stronger, but this is because of the fact that in the examples, well, the only technique that we were really using at a level of G prime was only the existence of a joint distribution. And the fact that when you have nodes with disjoint causal paths, then they're independent. So this uses really very little at a level of G prime. And so the inflation technique leverages that to something quite powerful at a level of G. Yeah, so yeah, it amplifies the power. Oh yeah, okay, I guess I've already said these things. So at a level of G prime, in the examples, we've only used the existence of a joint, and that nodes with disjoint ancestry are independent, or have independent distributions. So we obtain inequalities or constraints that do not just follow from these things applied to the level at a level of G. But yeah, in principle, one can apply whatever your favorite method for causal inference. You can plug it into this black box, and you probably get something that's gives you stronger constraints, tighter constraints. Okay, so there's another, using, so for the injectable sets, we know explicitly directly that the marginal distributions are the same as on G. And this condition we can apply to the sets that we call AI expressible. I guess, so the II is here standing for ancestrally independent. Well, in this session one might think it stands for something else, but so AI expressible means that it's union of injectable sets having disjoint ancestry. In this case, we obtain that factorization. There's a bit of a more general set, so this is a clumsy term, but the reason that for using this term is that there's a more general concept of expressible set, of which these are a particular subclass. And the expressible sets are precisely those for which one can compute the marginal distribution on this set from the given distributions on the injectable sets. So for example, an injectable set is expressible. We can write down what its joint distribution is. Oops, sorry. Any subset of an expressible set is certainly also expressible. And whenever you have three sets which satisfy a d-separation relation, so this is this jargon for the fact that in any causal model on G prime, C makes A and B conditionally independent. So if we have such a d-separation relation for three sets, and we know that what the distribution is on A union for the nodes in A union C and for the nodes in B union C, then we can apply that conditional independence to also write down what the joint distribution for the nodes in A union B union C is. And so this having disjoint ancestry case is the special case of this where C is empty. So the family of expressible sets is precisely, well, a set is expressible if you can basically generate it by some number of applications of these things. It turns out that a second condition is actually necessary. It's not redundant. When I was thinking for a while, well, this is probably not necessary to get. But
expressible sets is a kind of closure of.
Yes, exactly. Yeah. Yeah, and there are also examples of expressible sets that are not AI expressible. So sometimes using these conditional independences for non-MTC gives you strictly more. So it's somehow a more complicated definition, but yeah, it is more powerful. Okay, so in principle there's many methods now that one can apply at a level of G prime. But yeah, as I said already, using merely the existence of a joint distribution for these marginals on the expressible sets goes quite a long way. And in this case, the problem that one has to solve is what's called a marginal problem. So you're given a family of marginal distributions, and the question is, well, is there a joint distribution that marginalizes to these? And so now this is just linear programming, a linear programming problem. Everything is linear, because marginalization is a linear operation. And one can also, so this is very easy to do in practice. And if you want to have constraints, so if you don't have a particular distribution to look at, but you want to know inequalities, that means then you need to basically enumerate all the facets of the corresponding polytope that you get when you start with the probability simplex of all the joint distributions and project it onto the space of all these marginals. And so this is called a marginal polytope. And just, well, you enumerate all the facet inequalities, and I mean, there are standard tools to do that, although it's not an easy problem in general. But we've done this in some cases. Okay, so here are the results for doing this facet enumeration, and so deriving all the inequalities for a particular inflation. Namely, the inflation graph that we looked at is this one for the triangle, and then we get here a bunch of polynomial inequalities. This is now ordered by degree. So the first line, except for this one, the first line of each inequality are the terms that are linear in the probabilities. The second line are the quadratic terms, and then the third power. And yeah, so this is the inequality that I had shown earlier, and these are just more complicated ones. Yeah, I don't really know what to do with these or how to interpret these.
Because, well, yeah, you have the marginal problem, as we have seen to that. On one side, that you have like a linear application that represents like the marginalization, and you can just solve that. So in general, that will give like a family of solutions that are not necessarily positive. So they are not necessarily probabilities, and that's it. If you just do linear programming, you have no guarantee that what you obtain is a probability measure. It's in general just a collection of. No,
you do. I mean, these are the constraints. These are in.
So this is related to like discriminating which of these solutions are probabilities and which are not probabilities.
Oh, I see. Which, yes.
Why are you writing this now? This down. That's my question.
Yes. Okay. So so we're asking, when is a given family of marginals? When does it arise from some joint distribution? When does there exist a joint distribution that marginalizes to these? And now, if you look at the set of all these families of marginals that do, these form some polytope, because it's just marginalization is linear, so it's just a projection of the probability simplex under these marginalization operations. And in general, this is quite a complex polytope. It has many facets.
Okay. So your equations describe this polytope.
Yes. These are, there are many more facet inequalities of the polytope, but each facet inequality this is a linear inequality for these it's a linear inequality involving these marginal probabilities, which are so the variables of this inflation graph, the observable variables of this. And now I substitute these equations into the inequality, basically. And that's how they become polynomial.
This is a kind of approximation to the polytope that depends on your inflation. I mean, like each inflation gives you some...
It's an exact description of the polytope, and it's an approximation to the set of all distributions P, A, B, C that are compatible with the original causal structure. Yes, exactly. It's not a polytope, because now we have nonlinear inequalities.
Okay.
It describes some kind of semi-algebraic set, One good way to see that it's not a polytope is that every deterministic distribution is compatible with the causal structure. So if it was convex, it means every distribution was, okay, so yeah, these are the particular, I mean, the facet inequalities are actually a lot more, but...
these are some inequalities of the marginal facet, right?
These come from, these I get by taking these facet inequalities and so doing the substitution. And then the original list is actually a lot bigger, but then, I mean, there are plenty of symmetries that lead to reductions. And also some of them turn out to be redundant. So this was done just by numerical optimization. You can check which one of them are actually necessary to bound the set of P, A, B, C's. And most of them turn out to be redundant. These
are not linear, so they don't
right.
define spaces. They define the invariant polytope, which describes the model. These are like the equation that gives you the curve in the representation of the independence model within the probability sequence, right?
Yes. Well, an important difference to the restricted Boltzmann machines is that here I'm not putting on any constraint on the number of values that the hidden variables can take. And this is in some sense also actually what makes it difficult, what makes the problem more difficult, I think, in some sense. I guess our results are saying that really it's simpler than, but a priori one may think that it's more difficult.
But why inequalities? Why you have inequalities and not equalities in this equation?
Because, yeah, well, if you take a look at the original triangle causal structure, there are no equations. There are, so to be, first of all, you can see there are no independences because there, in general, there are no conditional independences. And in fact, the achievable distributions, let's say with binary variables, the uniform distribution is achievable. And also there's an entire open ball around the uniform distribution that is achievable. So there cannot be any equations. So you can only basically find inequalities that bound the set from the outside. Okay, so these are the inequalities that we get from that particular inflation graph. Now the question is, well, do we actually get a complete description of the set of distributions that are compatible with the graph? And this seems like a really difficult problem. And so I personally really didn't know how to go about it. But now, just recently, my co-author and somebody else proved that the set under an additional, using additional constraints on G prime that I'll explain in a second, the inflation technique is complete. So whenever you have a distribution that is not compatible with the causal structure, our technique can detect it. So this requires a little bit more than just using the existence of a Turing distribution at a level of G prime. Namely, this is really the main additional ingredient here. These are just additional linear equations. So if we go back to the spiral inflation here, and if you now assume that you have such an inflated causal model that comes from a causal model on G, then also the distribution of A1 and Y1 is going to be the same as the distribution of A2 and Y2, just because we have the same data there at those nodes. And so this is an additional linear equation that one can use in addition to the non-negativity and to the existence of a Turing distribution. So this leads to a smaller polytope, to some kind of section of the marginal polytope. And if you also use all equations of this type, then in the case of the triangle causal structure, they proved that then the inflation technique is complete. And every non-compatible distribution will be detected. And so this applies in general to in all those cases where the causal structure has these two layers, like in a restricted Boltzmann machine, of an observable layer and a hidden layer. And they also proved that one can always reduce to this case by an additional technique, which is something which is related to, and I think we have some experts here into Pearl's counterfactuals, which means that you take, let's say you look at this, or this is the original graph, so in this case we have more than just two layers. But what one can do here to kind of make it into something like two layers is that you just create two copies of x. You kind of cut x apart into the actual value and some additional x prime that is sort of a counterfactual value. And then whenever you have a chain distribution on this, you get a family of, or you get a space of chain distributions here. And then one can work at this level, and then their completeness proof applies. Okay, yeah. So this is the result from this paper. If you use these two additional techniques, then inflation solves the problem of causal inference with hidden variables completely. And so the main ingredient of the proof, which may be of independent interest, is a kind of definitive theorem for these causal networks, Bayesian networks, which are of this restricted Boltzmann machine type. Maybe this is already known among people who study restricted Boltzmann machines. Yeah, might be good to hear about that, and I would tell them. Okay, now let me get to a bit more speculation towards the end, namely entropic inequalities. So there's some hope, maybe it's a bit more wishful thinking, that one could use also these techniques to derive entropic inequalities. So let me give a brief introduction. So when you have a bunch of random variables and you look at the entropies of the chain distribution and the marginal distributions, those are not completely unrelated, right? But there's inequalities between them, in particular, so the submodularity inequality or strong subadditivity. But there's also more complicated inequalities that do not follow from the ones of this kind. So these are called non-Shannon type inequalities. And these are kind of pretty difficult to get your hands on. And it's as far as I know, it's an open problem to find a complete list. Even theoretically, to find some procedure that could generate a complete list or something. And now the standard method for deriving such inequalities is what's called a copy lemma. And in a sense, this is now really a very simple observation, but what I want to explain is that you can view this as an instance of the inflation technique. So by starting with a graph like this, you take some chain distribution for A, B, and C, and you put some hidden variable in between, and then one can look at an inflation graph that looks like this. So where the x has been duplicated. And now if you look at a chain distribution here of A1, C1, A2, and B1, then this is the same distribution as one constructs from the copy lemma. And now one can use the standard entropic inequality, Shannon type entropic inequalities at this level in order to derive non-Shannon type inequalities here. And so it kind of feels like this is really, the flavor of this is really pretty much the same as the things that I was showing earlier. And so what I'm hoping, but what still hasn't worked out so far, so one can try to derive new entropic inequalities using more complicated inflations. But a challenge, I don't really even know how to start, because here it seems like one should start with some causal structure that can represent any chain distribution, and then find some interesting inflation of it. And well, pretty much the only example that I know is something like this. So that's how far I got so far with this problem. Okay, one can also apply the method to other types of networks. I mean, because the idea seems quite general and abstract and not really specific to probabilities. I mean, the completeness proof seems specific to probabilities because of the definite theorem, but the general technique seems fairly general. And so I was thinking and writing this in the abstract, that one could also try to apply to neural networks. And so given some function and a given shape or of a neural network, can you compute it? Or in other words, just a circuit diagram. Is that shape of the diagram capable of computing that function? And here, the technique actually does not apply. I can say a little bit more about why. Well, it does apply, but it turns out to be trivial. There may be other applications. Yeah, I haven't really explored restricted Boltzmann machines yet. I mean, here what makes these different is the fact that also the hidden variables are constrained to be binary. Right? And so really one would want to use something additional at a level of the inflation graph G prime, which takes that into account. And one could try to do that, but so far I'm not sure. Okay, phylogenetic trees. That again is just pure speculation. And may as well be wishful thinking, but maybe this would make it closer to what then linguists and also evolutionary biologists do. And finally, let me say concerning the level of generality, what I do know, besides these applications which I haven't explored, but in the abstract, I do know at what level of generality it applies. Namely, whenever you work with networks in a monodal category, for maybe some of you, for those of you who know about monodal categories, whenever you work in a monodal category where systems can be discarded, which means that the unit object is terminal. So this gives one variant of a generalization of the inflation technique. And a stronger variant you get when systems can be copied. So in my original two examples, here I only took copies of the original things and rearranged them. And I had to discard something. So for the y2, I had to discard one of these two systems that are outgoing or that one can think of flowing along these arrows. So this is the first variant, one can generalize this. And the second variant, in the spiral inflation, I've also used the fact that I can copy the values of these hidden variables. Okay, so this will be the general thing. And yeah, I think I'm done. Thanks.
Thank you very much. Are there questions?
Sorry, something I don't understand. The spiral graph, okay, it solves the problem for a family of probabilities of the three variables. Okay?
Yes.
But not for all. Not for all of them.
No, it solves the problem for all of them. But the inflation graph that you have to look at may vary.
Yes, that's the question.
Oh, I see. Sorry.
Do you have tried to
I think
determine the decomposition of the 7 simplex in pieces where you can choose such an inflation graph? Because the inflation graph, in the sense, it solves the problem often. Okay.
I think so. So it may be this is work in progress, especially by my co-author. Who it may be the case that for the hidden variables, you only need to assume a finite number of values that they can take, a given fixed bound. And if that is the case, then it's enough to look at one fixed inflation that does everything, that detects everything. But this is preliminary. So I don't want to claim this with 100% certainty.
Think.
But in this case, the answer is there's one is enough.
There's a finite number is sufficient.
Probably, but yeah, I don't want to think I don't want to claim this at the moment. Haven't checked it myself.
Thank you.
I have a question or comment to your last speculation topic. It's this information inequalities, non-sham information inequalities. First comment is I think that Ferro showed that actually the number of these inequalities is infinite, I mean facets, so that therefore the cone, entropy cone for n equal to 4 is not polyhedral.
Yes, I'm aware of that. I think even not semi-algebraic, right?
Yeah. And the question is, well, you consider that for deriving your technique, inflation technique for deriving new inequalities, non-sham, have you also considered for deriving its, say, conditional, inequalities that they assume some conditional independence, because these are important for deriving some conditional independence statements. Yeah,
no, we haven't tried that yet, but that's definitely something interesting to do. But then, maybe I should ask you more about that. Yeah.
Let's thank the speaker again.